Hi, thank you all for being here. Today we will be going over our poster for the redesigning of a frame rail denesting operation for Daimler. The idea here is to understand the problem. On the left side, for the current design, we can see that if a bolt is in the way of the magnet, none of the magnet can have sufficient contact with the rail. On the right side, we came up with a design that with a rod, so if there is a bolt in the way of the magnet, it will be pushed up without impacting the other magnet, and two magnets will be sufficient enough to hold the rail.
This design uses the existing magnet mount with a minor change so it'll fit the machine the same way it currently does. We are only implementing this on the top two magnet mounts. It is easy to implement, easy to maintain, and easy to repair. The parts that we are using is a 1-inch linear guide rod that's threaded into the magnets, polyurethane tubing for compression, a washer to support the polyurethane tubing, a steel bearing housing which is bolted to the plate using a 3/8 socket head screw, with an oil embedded flange sleeve bearing. The grade 8 nut is holding everything together. The magnet mount plate consists of a hinge plate, long and short gussets, and a base mount plate. How it works is that the rails right now fall off the machine due to the bolts being in the way of the magnet, meaning it doesn't allow it to properly magnetize. The design allows for the magnet to be attached that will be attached to the bolt to compress while the other two magnets are able to attach to the rail.
There are a few risks associated with our suspended magnet design, the first of which is the change in magnet height. This could require changes to the PLC to accommodate for the magnets hanging lower than they did before. The second is the lifespan of the polyurethane springs. The team has created a polyurethane spring deflection calculator in Excel and EES that could be used to calculate the deflection of the polyurethane tube springs. If a harder or softer durometer is required to increase the lifespan of the spring, then this calculator can be used to get the correct dimensions and deflection value of the new spring. The biggest risk with the design is the potential for misaligned guide rods. The sleeve bearing mounts will be manufactured with loose screw clearances to allow the mounting blocks to align with the guide rods without binding.
In terms of the bill of materials, our total price is $1,304.79. Our most expensive part, the linear guide rods, at $391.56. We're going to be using 12 of them. They're the most expensive part, mostly because they are such a niche item, as well as them being a custom part for our specific design. Those will be coming from Izumi. We're also getting parts from McMaster-Carr, and Speedy Metals is where we're getting most of our steel. And the polyurethane tubing is coming from Polyurethane Products. For the implementation roadmap, we'll begin with purchasing parts, move into prototyping, then fabrication. We'll actually implement the design, and then we'll have a control at the end of the semester.